Okay, so in this video, we're gonna try and find the expression for I sub l of t for t is greater than or equal to 0. Now, right here in red, I wrote the expression for the charging of our inductor for t is greater than 0. Now, what the things we need to find in order to write this expression are I initial, I at infinity, and tau, which is this equation right here. So, in order to start, we are first going to put the circuit in the position that it is at t is less than 0. So, if we look at our switch is opening at t equals 0. So, at t less than 0, it is going to be closed. Now, if we look at our circuit, we see that this wire is in parallel with this resistor, meaning that it is practically going to be canceled out because the current is going to take the path of least resistance. It is also good to note that since our circuit or our switch has been closed for a long time, our inductor is going to act as a wire. Since the change in current across it is 0, meaning that voltage is going to be 0 because the equation for a inductor is L di dt. And when there's no current, there's no voltage. And when there's no voltage, it acts as a wire. So we can get rid of this inductor and place a wire. Now, it makes our circuit a lot simpler. So first thing we see is that all of our current is going to be going through this wire right here. And we have created two loops. One loop right here and one loop right here. And if we look closely, the current along this top wire is going to be 8. So we can say that our I initial is simply 8. Initial is 8 amps. Now we have to find t at infinity, or I at infinity. So if we paste our circuit again, and now we will put the switch in the open position because I at infinity is just t greater than 0. So now we will find the current along this inductor at I at infinity. So since our switch has been opened for a really long time, our inductor will yet again act as a wire. So we can replace our inductor with a wire. And now we will calculate the current going across this wire in this state. So now we have two loops. One loop right here and one loop right here, which means we can do mesh analysis. So when doing mesh analysis, we're using KVL, where rise equals fall. So as we see, going around this loop, we have one voltage source. And again, we'll label this A and this B. So to start off, we'll start off with this 12 ohm resistor. So we'll have 12A, 12A plus, and this is fall equals rise, rise. So everything on this side of the equation is going to be fall, everything on this side will be rise. This is because resistors naturally are fall, so it'll be plus, minus. And that is because we are doing our loop in this counterclockwise motion. So since this is a rise, it's going to be on the other side of the equation, 32. And now we have this 8. 8a minus 8. And then our equal sign. And also, this shouldn't be b. This should be just be 8 because we already know the current going through here. Okay, so now let's solve. So we will get 12a plus 8a minus 64 equals 32. 32 plus 64 gives us 96. So we can find these. 20a equals 96. So a is going to equal 4.8. So our current at infinity is going to be 4.8 equals 4.8 amps. So now we need tau for or at t is greater than or equal to 0. So this will be in our switch in the open position. So when our switch is open, we're going to look at this circuit right here. So when our switch is open, our inductor actually makes simpler. I'll just place a new circuit. So when our switch is open, we can see that our inductor sees our 12 resistor and our 8. To help with this, to help visualize this, we can shut down our current sources, which will make it a bit more visible. So you'll see our 12 and our 8. So, and those are in series, so we'll have 12 plus 8 equals 20 ohms. So our R equivalent is equal to 20. So now, to calculate tau, we do 0.005, 0.005 divided by 20. And when we do that, we get 2.5 times 10 to the negative 4. So now, we have everything to make our expression. So, I'll write this in blue. Let's look at our expression right here and just simply plug everything in. So for I naught, we got 8. So we have 8 minus 4.8 e to the negative t over 2.5 times 10 to the negative 4 plus infinity. So plus 4.8. Now we'll do 8 minus 4.8 to get 3.2. 3.2. Write that in blue. 3.2 e to the negative 2.5 times 10 to the negative 4 plus, should be, what did I erase here? 4.8 plus 4.8. And this right here is going to be our answer for this problem. Now, another way we can write it is moving this, our tau, to the top, which is how it's written mostly. So again, and we'll move this 4.8 to the other side. 4.8 plus 3.2 e. And then we'll do the inverse over 2.5, which is 4,000. So we'll get negative 4,000 t. And this right here is going to be our answer. So now for the next part, we are going to find the expression for v naught of t for t is greater than 0. Now we are going to follow the exact same steps we did before to find, like we found the current expression. So first we'll start with, we need to find v naught, or initial v, and to do this is quite simple. So for when t is less than 0, our switch is closed. Now, if we remember from the previous part, when this switch is closed, we have to realize that this wire is in parallel with this 8 resistor. And when a wire is in parallel with a resistor, it completely cancels it out because the current is going to take the least path of resistance. So our initial voltage is going to be 0. So now we have to find the value for I at infinity. So to do this, I will paste a new circuit in so that we can modify it. So this time our switch is going to be open because when t is greater than 0, it's in the open position. So now we can do mesh analysis. So we'll draw a loop here, and then we'll draw a loop here. Now we'll start with this 12 ohm resistor and label this A. And then we already know this is 6 amps. So we'll start with 12A plus, remember, when using mesh analysis, it is KVL, which is fall equals rise, because resistors naturally fall from plus to negative. So this 32 will be on the other side of the equal sign. So then we'll move on to the 8. So plus 8, A minus 6. And then remember, this inductor acts as a wire because we are getting the voltage at infinity. And after a while, the inductor will act as a wire. So equals 32. So then simplifying, 12a plus 8a minus 48 equals 32. So then we'll add like terms. We'll get 20a equals 32 plus 48 gives us 80. And then we get a is equal to 4. Okay, so now that we have 4, we want to get the current that is going through right here. And to do that, we want the current in, not that direction, this direction. Actually, no, this direction, because we want to go from high to low. So we choose the one where it's agreeing with the direction, 6. So we have 6 minus 4 equals a current of 2. So now we just do simple V equals I, Ohm's law, V equals R, Ohm's law. And when we do that, we get a infinity voltage of 16. And we already know tau from the previous problem. Tau is still going to equal 2.4 times 10 to the negative 4. So we are ready to create our expression. And remember, I will write down the expression again. And this time I'll write just a general expression that you can use for either voltage or current, because they're pretty much the same. So we have V naught minus V, or no, I want a general one, so X naught minus X at infinity, E negative T divided by tau plus X infinity. So this is the general equation that you can use for either current or voltage. So knowing that, let's write our expression for voltage across that our 8 ohm resistor. So as for our initial, we found we got 0. So 0 minus our infinity, which is 16. Put this in parentheses, e t. And remember, we found that to be negative 4,000 t plus 16. So simplifying this, our voltage is 16 e negative 4,000 plus 16. And right here is our answer. And remember, this is negative 16. Forgot to put that there. Okay, so next we're going to find v sub l at just after 0. So basically, if we look at our circuit in our corner here, we see that we are getting the voltage across the inductor. So to do this, we will be using the equation V equals L times di dt, our voltage equation for an inductor. Now we already have our current across our inductor, which is right here. Except that we will be using a different one because we used a different equation. So I'm going to draw a new one. So the equation that we will be using is going to be 4 plus 2e to the power of negative 4,000 t. So we're going to be using this equation to solve our answer. So when using this equation, we are just going to plug it in for our di dt. So, and also we'll plug in our L while we're at it. So V is going to be equal 0.005 times all of that stuff that we put in yellow up there. 1, 2, 3, t d over dt. So now we will take the derivative of all of this, and when we take the derivative of 4, it becomes 0. And when we take the derivative of our exponent right here, of our e, we bring down the 4,000, multiply it by our 2, to get negative 8,000 times e to the 4,000 t. All of that times 0.005. Now we want our v right after 0, so we are going to plug 0 into our t. So I'll rewrite the equation. 5, negative 8, 1, 2, 3, 1,000, 4, 1, 2, 3, with a 0 in our equation. And now we will plug all of that into our calculator to get a v value of negative 40.